Question 6 then, from the 2022 mechanics paper. Format question here for, by the looks of it, use calculus to show that the basic derivations you would get at the beginning of a dynamics course. Well, what normally happens at the beginning is you start with the most elementary one, which would be the displacement, the distance. And from that, you would get the velocity, we'll just call it speed just now, which is the rate of change of distance. And from that, you would get the acceleration, which is the rate of change of the speed. So those are the basic definitions. So if you're wanting any further ones, you would use those basic definitions. So in part A, it says this. Well, it's also got a couple of initial ones, because with speed, you would use u for the initial speed, and for distance, it would generally be s0 you would use for any initial displacement distance. Well, A, use calculus to show that v equals u plus at. So you'd be starting with this one here, because that's the one that mentions v and a for 2 marks. So starting with that one, if a is equal to dv by dt, then shuggling them about, dv would equal a times dt, and that's what you would integrate. I don't think you get, I'm not sure when you get this, when this mark pops out. No, it doesn't pop out until you finish. So now there's 2 ways you could integrate that. You could integrate that and introduce a constant, or you could integrate that between limits. So I'll put them side by side. So you can either just go ahead and integrate that, so that'll go back to v, and that'll go to at plus c. Or here you could say, well, the acceleration's constant. So I'm going from time 0 to a certain time. Now there are conventions whereby you can't use the same letter, for the integrand and for the limit. You'd have to change the style of lettering. We'll just understand that we know which is which here. And the velocity would go from an initial velocity, which is u, to the final velocity, which is v. Again, just allowed ourselves to use the same variable. So in this case here, you'd say, well, how would you find c? Well, if we're assuming that, in this case, I'll just put it down here. When you start at that velocity, and a is constant, but the time is 0, so we've got at time 0, the velocity is u, that would be 0 plus c. That just says that c is equal to u, so here's your formula. v equals u, but I'll put that first, plus at. So the marks were integrate it, introducing a constant, use initial conditions to get the final form. The alternative way, which doesn't need a constant, is just to integrate that up. So that would go back to v, from u to v, and that would go to at, although a is a constant, it could just pop out, from 0 to t. So what that says is v minus u equals at minus 0, so v equals u plus at. So that would get the first mark, and then same as before, that would get the second. So in part B, hence, so we've already derived this, so we must be using that. Hence, derive an expression for its displacement, s, from its original position. Now, I don't think it means the original position, s0. I think it just means using 0 for the starting position. Well, again, using the basic definitions, this is the one that connects v and s. So rearranging that would have ds equals v dt, which from that then becomes, I'll just still put it down here, ds equals u plus at dt. Then integrate that up. 2 different techniques again. Introduce a constant or use limits. So introducing a constant would be, that would go to s, u to t, remember u was a constant because that's just the initial velocity. A is a constant, all these equations just apply to constant acceleration situations. But t, that would go up to t squared, so half at squared plus c. Now, what do we know? We know that t is 0. At t is 0, we're just saying the initial displacement is 0. Because if there was an initial displacement, then that would be an S0. So using the 0 would give you 0 equals 0 plus c. In other words, c is 0. So now you've got S equals u plus ut plus a half at squared. So that would be the first part, integrating it, introducing a constant, and then using s equals 0. Here it would be the time goes from 0 to t, the distance goes from 0 to s. So you've got s going from 0 to s of ut plus a half at squared, integrating it up over t, goes from 0 to t. So you've got s minus, well, I shouldn't have put that in, I've done it now, equals ut plus a half at squared. I'll just put minus 0. So s equals ut plus a half at squared. So introducing limits, integrating it. When we know if that initial displacement hadn't been 0, you'd have called it S0. So what would have happened here is that that would have been replaced by an S0. So this would have read S equals S0 plus this. Similarly here, it'd be S minus S0. So S equals S0 plus that. So we're just taking it as measured from the initial position. One last thing, in the marking scheme, it doesn't start from this basic definition. In part B, I don't know, it's interpreted hence as starting from this. If you were to start from that, then all you could do would be integrate that. So if you did integrate that up with respect to t, well, obviously that's just the same as that. So that part would just follow in as normal and you'd get your constants and so on. But you'd have to do some rearrangement to show exactly what that means. So what does that mean? Because that's not a basic definition. That's the basic definition. You'd have to rearrange that. You would have to show, I would have thought anyway, that since v equals ds by dt, then v dt is equal to ds, so that integrating it up produces s. So I've put down the one starting from the two original definitions.